Oh, whoops. I should also test to make sure that my audio is going in. Okay, my audio is going in. Okay, great. Excellent. All right, so does anyone have any questions before I start? If this fails in any way, I apologize, but hopefully it will be fun. No? Okay. So this is chapter 1, introduction to the human. This is just chapter 1 that's in your book. Anyone recognize the diagram, by the way? Yeah, it's a Pokemon. Yeah, it's Bulbasaur. See, it's got plants growing out of it. Yeah. So, yeah, I just thought it'd be fun. I was trying to include something fun on the PowerPoint. Okay. So, chapter 1 is over a number of things related to the overall organization of the class. Most biology classes start like this. They start with the definition or organization of life itself. We are going to be talking about levels of organization. All matter in the universe is made of chemicals, atoms, matter, and these chemicals are arranged into cells, and cells are the smallest unit of living things. You'll read this in biology books all the time. I remember learning this when I was in biology, and I never thought it was very I was like, why are we so excited about cells? Who cares about cells? I think they're dumb and boring. And much later on, I finally understood what was being communicated to me. This is what's cool about a cell. Imagine a car. A car does a bunch of things. Imagine all the things that a car can do. Right? It can drive. It can stop. It has wiper blades and whatever. Maybe all those aren't necessary for it to be a car, but a car does a certain number of things in order to be defined as a car that works. Right? That car is made of parts, and those parts are not cars, right? The engine is not a car. Wheels are not a car. The frame is not a car. The axle is not a car. The carburetor is not a car, right? Only when you put them together is it a car. But you have to put them together the right way. If you just take all the parts of a car and just put them in a pile, is it a car? Of course not, because it doesn't drive anywhere. You have to put it together just right. And if you take away one piece, important piece, like the engine, is not a car anymore, right? You take away a window, I mean, you can argue about that, right? So, cells are living things. They meet all the definition of living things. And tissues are made of cells, and tissues are also defined as living things. And organs are also defined. Your heart is alive. Your pancreas is alive. Your spleen is alive. Your bones are alive. Here's the thing is that the cell is made of stuff that is not alive. Water is not alive. Protein is not alive. Fats are not alive. Some members are not alive. And if you just take a pile of protein and water and just kind of shake it up, it's not alive. Only if you put it together in the right way does it become alive. That's really cool. That's why cells are so interesting. Because cells are the thing in our body that is alive that can make new things, that can build new parts to our body, that can grow, that can make more cells. You can't do that with a pile of protein. You can't do that with a pile of fat and water and salt and vitamins. None. It doesn't work. But if you put it together in just the right way to make a cell, that cell is alive. And if you put those cells into tissues, the tissues are alive. Tissues can grow. Tissues can heal. Tissues can change. If you put those together in organs, those organs can grow and change. That's really cool. But, only the cells are what are make up life. And cells are made of chemicals. When chemicals are really cool and interesting and useful, we're going to study them, but those aren't alive. The cells are alive, then they make up tissues, and those tissues make up organs, and the organs are put together into organ systems. These are all living things. But they're made of chemicals. Like water, for example. And here's a fun thing about water. Think about this for a second. I don't know if you ever heard of the paradox of the ship of Theseus. This is a fun one. If anyone's ever taken a philosophy class, you might have heard this one. So here's the idea. Here's the setup. Theseus was a Greek hero in mythology, ancient times. And they told the story that he went on a quest, a 20-year, long journey. He got in his boat and he left. And then one day, a board broke on the ship, and they had to, to get a trade for a new board. Rope broke, they had to replace it. The mast broke in a storm, they had to chop down a tree and replace it. The sail tore. 20 years go by, he comes back home to wherever he was from, Corinth, I think, and every piece of that boat had been replaced. Was it still his ship? Was it still the ship of Theseus? And ask yourself that. You would think yes, but then what is a ship? Because the ship that left and the ship that came back are not the same material. There's not one piece of wood. He had to trade for a new anchor. He had to do everything to replace every piece of that boat. The caulk, the everything. He had to replace all of the different parts of it. What is this ship? And here's the thing. We're made of molecules. But every day we take in new molecules and excrete out molecules. Every day we drink water and we excrete water. We breathe it out. Right? We urinate it out. We're made of molecules, but those molecules are come and go. Our cells die and are replaced. We have stem cells that grow new cells out of food that we eat. So what are we? What are you? That's an interesting question. That's a little bit beyond the scope of this class, but I just thought I'd put it in there just because when we approach biology, what you're going to see is a lot of the assumptions we have about ourselves, about how the world works, are not true. Because you are constantly replacing your molecules, yet you feel like the same person. God, well, then what are you? What is you? Just a fun question for you to keep you up late up at night, right? So, a cell, now we define life. There's a bunch of different definitions of life. I've seen professors who test which of these is not one of the criteria for living things. And there's also a list of 8 things. And that gets to my nerves. Because, first of all, you're overcomplicating it. And second of all, this is an A&P class, not a general biology class. So, I'm boiled down living things as to they do these 3 things, right? Living things in some way have a metabolism, and that means that they take in materials, use them up to create energy to rebuild their parts as they wear down, and then excrete the waste. That's metabolism. That's what we do. We eat food, and then we excrete the waste products in order to keep our energy up, right? And our cells do this too. They do it in a different way. They take in glucose, they excrete carbon dioxide. They use that energy from the glucose to rebuild their cell parts, right? But that's metabolism. That's something that living things do, and living things generally do not do. The ability to reproduce, right? Now, we, of course, as a human being, can make more human beings, unless we happen to be missing the parts for any reason. But in general, most humans are able to do so. Our cells, at some point in their life cycle, in their stage, were able to reproduce, to undergo mitosis, although our adult cells, like our skin cells, for example, they're dead. They're not going to make any more cells. But at some point in their life cycle, they were. And then they have to maintain homeostasis. That's my first vocab word we want to make sure we learn. Homeostasis. Now, I'd like to point out that living things do all 3 of these. Things that are not alive may or may not do 1 or more of these, but they don't do all 3. So, for example, crystals grow. Crystals grow and reproduce, but they're not alive. That's just a chemical process that happens in caves and stuff. All right, so homeostasis is a really important one. What is homeostasis? Have you heard this word before? Yeah, exactly, right? So maintaining the balance in the body somehow, right? And the way that homeostasis is maintained is with feedback loops. But here's the trick with feedback loops, because I've taught feedback loops. We're going to see a bunch of feedback loops throughout the semester. I teach them, and people on day 1 are like, I don't get it. So here's the trick with understanding homeostasis. Maintaining a balance. Of what? That's the trick. Different living things maintain homeostasis of something. Now, the easiest thing to understand, this is how we know feedback loops. Let's look at temperature. This is the one we all can tell right away and identify with. So let's say I want to maintain homeostasis of temperature. That means I want to keep my temperature at a certain amount. What amount of temperature do we humans normally keep, by the way? What's our body temperature typically? 98.6, right? Thereabouts, right? So what happens then? So that's the idea. That's the goal. That's to set your body temperature 98.6. What happens if your body temperature goes up for some reason? Like if you walk into a hot room or walk outside and the sun's on you or whatever. What do? We sweat, right? And what does sweat do? It cools us down. That's a feedback loop. The reason we sweat was because of our temperature, but then the sweat changes our temperature. So the idea of a feedback loop is that I have something like an increase in temperature that increases something else, like my sweat, and that sweat is going to change my temperature. So it's a loop. See how one thing affects something else and that other thing affects the original thing? This is what's called a negative feedback loop. That's how we keep from getting too hot. The hotter we get, the more we sweat, and that cools us down. Also, we take off our clothes and we complain and we go drink some water. Those are all things we do to maintain homeostasis, right? Same thing but backwards. What happens if our body temperature goes below 98.6? We start to shiver, right? And we complain and we turn on the heat. And all those things are designed specifically to get our body temperature back up, right? So if my body temperature goes down, that's going to increase my amount of shivering. And that shivering is going to make my body temperature do what? It's going to go up, right? But notice this starts as a down, so it's a negative feedback loop because it's like a double negative, right? My temperature was going down, now it's going back up. So that's where we're at a negative, the opposite. These are negative feedback loops. And a feedback loop is anything where something affects something else that affects the original thing, right? So there's a bunch of negative feedback loops in the body. And that's how we maintain homeostasis. Temperature is the easy one, but there's a lot of other feedback loops. And every feedback loop maintains something at homeostasis in our body. So what are some of the other things that we keep at a constant amount in our body besides temperature? Anything else? Blood sugar, excellent. Anyone know the organ that helps regulate our blood sugar? Hopefully not the kidneys. That's the backup plan. Plan A is your pancreas. Releases insulin, right? Yeah, if your blood sugar starts going too high, you start peeing sugar out, right? That's backup plan. But yes, your blood sugar is regulated by your pancreas, which secretes insulin and glucagon, which regulate how much sugar is in your blood, right? And so that's also going to be a feedback loop like this. What are some other things that are the constant amount in our body? Excellent. Blood pressure. Exactly right. And that is regulated by part of your brain stem in conjunction with your heart and blood vessels. And it's also affected by your kidneys. There's a bunch of working parts. It can get really complicated. But the basic idea is if your blood pressure goes up, it makes your heart beat less, and then your blood pressure goes back down. Right? Same thing but backwards. Your blood pressure starts going too low. Your heart starts beating harder. Right? And that's what puts your blood pressure back up. That's why people, if they're bleeding out and their heart starts pounding, like it starts getting weak, but it keeps beating harder and harder because their blood pressure is going down, right? So all these things fit together. Anything else we keep constant in our body? Or within a range? What about the amount of water, maybe? Maybe the amount of salt, right? Things like that. Got to keep certain amounts of those things in our body. Got to keep the amount of calcium constant in our body. Right? All these things are regulated by negative feedback loops. Because a negative feedback loop is what will help keep something in a balance. So a negative, now, I'd like to point out very quickly that just because something is a negative feedback loop doesn't mean that thing is alive. So if you have a room with AC and a heater, and they're both set to 70, if the temperature goes up, the AC goes on, and it goes down. But the temperature goes down, then the heater goes on, and goes up to 70. That is a negative feedback loop. But that's not alive because it doesn't have a metabolism, it doesn't reproduce, it doesn't make more AC units and heaters. Right? That is just a room that is set to homeostasis. But our bodies do that dynamically. We have this system where receptors, parts of our body that receive information, send signals to control centers, like in the brain, like in your glands, like in other tissues. And those control centers will control effectors that cause you to sweat, right? That cause your heart to beat more or less, to cause you to secrete insulin. Whatever those things are that help keep your body in balance. That is homeostasis. That's what keeps our body at a certain amount. It's never by accident. And you can always go to your local hospital and find someone whose homeostasis has failed in some way. Right? Diabetes is a failure to regulate insulin. Right? You can see what happens when people have problems with their blood pressure, have problems with their kidneys, have problems with all different kinds of things. Because you want to keep something everything in your body has to be a certain amount of it. And that's maintained through negative feedback loops. And each of our cells has to maintain homeostasis as well. Each one of our cells in our body, except for the ones that are dying, because there's some that are dying, but all of our living cells are maintaining homeostasis, and they're contributing to the overall homeostasis in some way as well. All right. So I'd like to quickly point out that a negative feedback loop is how we maintain something in balance. You may occasionally also see a positive feedback loop. this can be a little confusing because the word negative usually we think is a bad thing, and positive is a good thing. But it's actually backwards in anatomy physiology because let's say I switch the wires in my brain, hypothetically. Let's say that I switch my body's perception of heat and cold. Right? Let's imagine that. So now when I get hot, increased heat, what will that do? What will I do in response? Shiver, right? This is not real. This is a hypothetical, right? I'm going to increase my shivering, and what will shivering do? Increase my heat, and what will the increase in heat do? Make you shiver even more, and then what's going to happen? It's going to keep going and going until I overheat, until I cook. Right, you can actually die from this, right? This is hypothetical. You can't actually do this to your brain. But if you could, this would actually kill you, right? Because a positive feedback loop builds up to some kind of endpoint. Positive feedback loops are powerful and they're dangerous, and there's not very many in our bodies. They're for amplifying effects, and they can overtake your body, and if they're not controlled. We see a few examples of positive feedback loops. The most classic one is childbirth. So, for example, what happens when a woman is about to get birth? The baby's head presses on the cervix, right? So, increase pressure on the cervix. And when you have pressure on the cervix, that causes the release of a hormone. Anyone know what the name of that hormone is? Oxytocin, right? So that's released in response to the pressure on the cervix. And the oxytocin causes uterine contractions. And uterine contractions cause the uterus to squeeze, and that squeezing causes the baby's head to press more on the cervix. Which then, since there's more pressure on the cervix, what happens? It releases even more oxytocin, which then causes the uterus to contract and squeeze even harder, which causes the baby's head to press even more, which causes even more oxytocin to be released, which causes the uterus to contract even more until the baby is born. Or until the baby and or mother die, which used to be a lot more common before modern medicine, and still happens on occasion, right? So, scary stuff. So this is a positive feedback loop. It builds up to an end point. Hopefully some kind of positive, happy end point, because it's definitely going to be a very powerful thing, right? We're not going to cover this in 24.1. I'm just covering this as a good example of positive feedback loops. We won't really see very many here. You'll see a couple more in 24.2. You're going to see this one, for example. Fun fact, fun side note, oxytocin, sometimes called the love drug, is a hormone that's actually associated with bonding and affection in your brain, which is why a woman can have another human being push through their genitalia for 24 hours straight, and when it's finally born, they immediately fall in love with it like it's the best thing ever, and not something that just ripped their lower parts in half. So it's really handy, too, because I don't know if you know this, babies are super annoying. We were all babies at some point. Oh, yeah, they are. Oh, come on. They are, right? You were annoying at some point, I bet. I know I was. I still am. You can make the argument. But luckily for oxytocin, our parents do not leave us in the nearest dumpster. They actually take care of us, which is great, because we're totally helpless for quite a while. So positive feedback loops build up to some kind of endpoint. There's not too many. We're not going to see too many in this class. We see them mostly. You'll see some of them in 24.2, which will be fun for you guys. I won't be there. I'll be here teaching 24.1 still, but it's fun. Okay, questions so far on feedback loops, definition of life, any of that stuff? So far, so good? Hopefully my laptop doesn't run out of power. I'll have to charge it up at some point. Okay. All right. So next on my agenda, anatomical terms. So this is an important thing, especially for most of you guys who are going on to, and I didn't get a close look at everyone, but it looked like a lot of people are going for RN, BSN, things like that. So most of you guys are going to be working in the medical field. These terms on the medical field are standardized. I'm going to mention them briefly. I'm going to test you a little bit on them on the test, but this is also in support of your lab professor who can also test you over them with diagrams. I know, by the way, I don't use pictures on my exams. That's your lab professor's job, to give you pictures and models and diagrams. I just kind of go over the concepts, so how you use these, we'll mention them here. It's really important to have these terms be standardized. So, for example, let's use a hypothetical imaginary scenario of doing a surgery. Let's say I'm a surgeon. I've got a patient on my operating table. I've got another surgeon on the same operating table. We're working together because it's complicated surgery. So I'm cutting and he's cutting and we're cutting through this person, and I'm busy, I finish on that. He's got a different angle. He says, hey, I need you to do something for me. I'm busy with this. I'm like, what? He says, I need you to cut down about an inch. I'm like, yeah, sure, no problem. So he meant cut down this way, like down like gravity, like down the body, down your chest. But I think he means down like gravity, like down into the table. So I go down an inch. I hit a blood vessel. Blood goes everywhere. Patient dies. We get sued. The end. Where did we go wrong? Yeah, it's not good terminology. What was the word? The word that he meant to use is this direction of the body. Anyone know the name for this direction on your body? Inferior, right? That's what he should have said. Inferior, right? I thought he meant down, like down into gravity, down. That would this way. What did I think he meant? Deep, exactly, or posterior, exactly, right? One of those terms. And so those are standardized terms. And then the other thing that's also standardized are the regional terms. These are also, I think I have another diagram later for the directional terms. But these are some regional terms. Now, there's a list in your lab manual of 41 of these guys. You're expected to know them all. That often intimidates people. They're like, oh my gosh, there's so many of them. How am I supposed to learn them all? Well, I have good news for you. Does anyone know what that's called when you type wrong on a keyboard, then your wrist hurt after a while? What's that called? What tunnel? Carpal tunnel. So what do you think your carpal region refers to? Your wrist. And look at that. There's one few you have to learn. Right? So actually, if you go through this list carefully, a bunch of these words are not hard. They're in fact easy because you already know them. What do you think this region is? Nasal region. Exactly. That's right. Good. You already know that one. What do you think this mouth region is? Oral. We already knew that word, right? From oral hygiene, brushing your teeth, right? That's what everyone knows that word from. Okay. So palmers, your hands, right? Digital is your fingers. So a bunch of these are already pretty straightforward. So yes, there are a few of these words that are weird and hard and new if you've never heard before. Like inguinal. Where's your inguinal region? Anyone know? No one knows? That's okay. It's a groin region, right? Anyone see inguinal? Yeah, that's what they say when they do that. No one says that. I'm kidding, right? So axillary is your armpit, right? Nuchal is the back of your neck. So some of these are weird. You never heard these before. But if you go through, there's only about maybe, depending on how much you read, about between 10 and 20 of these words that you've never heard before, right? A bunch of these you have. So that's one thing that you're going to be expected to do is learn all these terms and be able to use them, right? And then the directional terms, there's more terms here. These are actually not all in the lab manual. Most of them are, but olecramal is not, sacral is not. But the other thing, by the way, sacral, you're going to learn that eventually because a bunch of these regions, especially the ones you don't know maybe, they match actual organs. Like, for example, your sacrum is your butt bone. Your femur is your thigh bone. This is your femoral region. Right? And so the scapula, this is your scapula, this bone right here. So this region is the scapular region. So a bunch of these terms, they're going to come in later when you start learning bones and muscles because you are going to have to learn a whole bunch of bones and a whole bunch of muscles for this class as well. And this will help you with that as well. Notice that we've got superior, inferior. Superior is the word in anatomical position for going straight up. So if I'm standing on my head, that doesn't change which way is superior and which way is inferior, right? This way on my body is always superior, right? If I'm lying on my back or lying upside down or whatever, it doesn't matter. This direction is superior. This direction is inferior. What's the word for towards the middle? Medial. Good. And what's the word for away from the middle? Lateral, right? So when I use these terms, we need to be able to use them correctly. These are always relative terms, two things relative to each other. So if I'm in anatomical position, you could say my elbow is related somehow to my umbilical region. I should technically probably say, instead of my elbow, I should probably say my antecubital region is my umbilical region, right? So how are my antecubital region and my umbilical region related? My antecubital region, which is in front of your elbow, is lateral to my umbilical region, right? See it is. I can go a straight line and there it is, right? And so that means that this relationship, by the way, is reciprocal, which means my umbilical region is medial to antecubital region, my elbow, right? And so these terms can always be used in a reciprocal manner. My head is superior to my chest, therefore, chest is inferior to the head. Exactly right. Very good. Right. The one that people struggle with sometimes, your lab professor will cover this too, but I'm mentioning it now. Proximal and distal, that's on a limb. That's going along a limb. So I don't do proximal distal on my head or on my torso. But for example, if I compare my wrist and my elbow, how are my wrist and my elbow related to each other? My antecubital region is proximal to my carpal region, right? So, and that means my antecubital region is the one that approximates. It's closer to my shoulder, the closer to the attachment point. Distal has more distance. My carpal region is distal to my antecubital region, right? So that one, sometimes people get tripped up with that, so practice that one if you need to. I know your lab manual has some practice problems for those. And then some people mentioned earlier, superficial and deep. Superficial means towards the outside, right? So for example, my skull is superficial to my brain, exactly right. My brain, therefore, is deep to my skull, right? Exactly, right. And so inwards and outwards. Like my skin is the most superficial organ. My skin is superficial to my muscles, and then my muscles are deep to my skin, and my muscles are superficial to my bones. So these are terms. And then your lab class potentially going to have to learn the quadrants and where your major organs are in those quadrants, right? That there's actually an anatomage table in the lab the lab class you may get to play with. So that's all just organization of the human body, learning just how things are set up so that we have that language to communicate with later, right? And throughout the course and then also throughout the next class. You also want to make sure you know your body cavities, right? Now, the body cavities does not include your oral cavity or nasal cavity. Cavity, the word can just mean an opening. But when we say the body cavities, what we actually mean is these sealed internal fluid-filled spaces. Well, actually, there's a fluid inside the membrane between the two membranes. It's actually a double-layered membrane called a serous membrane, not a serous membrane. I don't know. It's just a different word. Serous membrane. The serous membrane is 2 layers of tissue with a fluid between them. And so this is your thoracic cavity, is your thorax, your chest. And then we have the abdominal or abdominal pelvic cavity for your viscera down here, right? So that would be your intestines and your kidneys and your liver are in your abdominal cavity. And so we're going to make sure we know our body cavities. This is out of, I think, your lecture book, but your lab manual has one as well. You can make sure you know the major organs in each of these, because we are going to cover the major organs in lab when you go over the organ systems. And because you're actually going to do a dissection, I don't know if you guys know this. I don't spoil the surprise for you guys. You do a rat dissection, actually see all the organs. You're going to make sure you know the body cavities before you get to that point. And so you can see there's actually the anterior cavity, thoracic, and your abdominal pelvic cavity. That's where your heart, lungs, and then liver, intestines, kidney, spleen are all located in the anterior cavity. The posterior cavity is your cranial cavity. What organ do you think is in your cranial cavity? Your brain, right? Exactly, good. And then also vertebral canal or vertebral cavity, which has your spinal cord. It's inside of your vertebrae. All right, so you're going to make sure this is a diagram. You don't have to, if you can't read this in the back, that's okay. This is in your lecture book, and also a version of this is in your lab manual. So you're going to make sure we know our body cavities, because that's going to come up again when you do dissections. And when we see where different organs are, we're going to have to know where they are related to our cavities. Okay. Questions so far? Questions? So far, so good? Doing okay? All right. Okay. So next up, or actually last thing for chapter 1, is I'm going to talk about the organ systems. There are many different organs in our body, and they are attached to each other, and they all work together. We have somewhat arbitrarily divided them into 11 organ systems. Now, that's not true everywhere. That's not a universal fact. I have actually seen the muscular and skeletal systems combined into one system. I've seen some other versions. And also there's some organs that are in more than one organ system, like your pancreas, for example. So it's a little bit arbitrary. But we do want to make sure we understand each of these 11 organ systems, because they have all these major working parts that work together to keep us alive. So first system on the left. Anyone know what that one's called? Yes, integumentary system is correct. The integumentary system is a fancy word for your skin, right? Which means you can always mess with people like, hey, your integument is showing. Cover it up, right? When you don't actually do that, that would be mean. Unless they know the joke, and it's like, right? I didn't know where Arabia. I don't know. So the integumentary system is very important for protection of our body from several things, from loss of water. It's actually waterproof. The keratin in our skin waterproofs our skin, keeps water from getting out, prevents bacteria from getting in, eating our flesh. Those are the main things you see with your skin. It's also for regulating our body temperature, as I mentioned earlier. Our sweat, which is what's supposed to happen when we are overheating, right? When I sweat, that sweat's going to decrease my heat, that sweating ability, and also not only sweat, but we have a lot of blood vessels in our skin, and they can get bigger and smaller. And so when they get big, our skin turns red and helps release heat from our body. That actually helps regulate heat. And if you're getting cold, especially internally, your blood vessels get smaller, and it helps retain heat, keep heat from leaving your body. That's why they say, now, we don't get a lot of snow here, but for those of you who may be familiar with snowy areas, you watch kids play in the snow, you're supposed to wash their cheeks, make sure their cheeks are rosy red while they're running around having fun. As soon as their cheeks start turning pale, then it's time to go inside and drink some hot chocolate, because the blood vessels are getting smaller because their core body temperature is starting to fall. So the integumentary system carries a lot of information, has a lot of functions in the body. Almost basically just about all these organ systems have multiple functions. You'll see they're all interconnected. It's a lot of fun. Anyone know what the system on the right is? Skeletal system, exactly right. Okay, so the skeletal system is important, obviously, for our bones, which protect our soft organs like our brain and heart and so forth are protected by bones. Our bones give us leverage, allow us to move around. Our muscles pull on them. But additionally, there's a mineral in our blood that has to be in our blood at a certain amount, or else we die a horrible death. Anyone know what mineral is very important in our bones? What's that? What mineral is enough? What's the number one mineral you're supposed to drink to get enough in your bones? Calcium, that's right. And so calcium not only is an important mineral in our bones, but calcium has to be a certain amount of it in the blood. If there's not enough calcium in your blood, you die a screaming death. If there's too much calcium in your blood, you also die a screaming death. But you never hear about anyone dying from that. You never at Grandma Betty's funeral. What happened to Grandma Betty? Oh, well, she just drank a gallon of milk. That was too much calcium for her. Her nerves failed, and she was screaming and writhing on. That doesn't happen. That doesn't happen to anyone. The reason for that is because our bones store extra calcium, and they release it whenever our blood needs it, and they trap extra to grow more bone density whenever we have extra. So you never hear about Grandma Betty getting too much calcium in her blood and dying. What you hear about is, what happened to Grandma Betty? Well, her hip broke, and she went to the hospital, and she never came home, right? Because Grandma Betty didn't drink enough calcium over the course of 4 years, and her bones got weak, right? So that's a real thing we have to worry about. But our homeostasis calcium, our bones actually help with that a lot. And we're actually going to see how that works when we get to the skeletal system in about a month. Okay, what's the system on the left? Muscular system, exactly right. Important for moving around. Also helps us maintain homeostasis of temperature, because that's what shivering is, right? Helps us move, interact with our environment, helps get food, right? Because most of us use our own hands to feed ourselves, right? So that's an important system for, and we're going to actually see how that works. We're just going to look at the actual histology of the muscles and how the muscles contract. It's going to be a big thing. What is the system on the right? Nervous system, good. The nervous system is often the control center for other organ systems, homeostasis. For example, I mentioned there are receptors in your blood vessels that measure your blood pressure. Those signals go to your brainstem, and your brainstem determines if your heart needs to beat harder or not, and sends signals to your heart to make your heart beat faster or slower, depending on what the blood pressure is. So again, a lot of the brain stem and throughout the brain, the hypothalamus, which handles your temperature, a lot of parts of the brain receive the signals from your body and then send signals back out to your body. And that's actually what we're going to be looking at with the nervous system, is this pathway of signals coming in from your extremities, from your flesh, going to the brain receiving these signals, processing them, sending signals back out to your muscles, to your glands, to your heart, things like that. And that's actually, believe it or not, those 4 systems are the entire semester. That's all we're covering in this class, one well, one of those four systems. Now we're obviously going to cover cells and tissues first and how chemicals work, and then we're going to get through the skin, bones, muscles, and nervous system. So then starting here on this slide, this is material you're going to cover in 2402. What's the system on the left? Endocrine system. Good. What is the... Now these organs all look like they're separated from each other, but they actually communicate with each other using what? How do they communicate with each other? They are glands, so what do? Yes, they create hormones. Hormones are molecules that go into the blood and bind to another cell and change its behavior, right? So, for example, testosterone, classic hormone, estrogen, classic hormone, they're released from one place in the body and they go affect other parts of the body, right? So those are other parts of the body change based on that release of that hormone. All of these are glandular tissues that release hormones. So pancreas releases insulin and glucagon, affects your blood sugar. The adrenal glands release a whole bunch of hormones, which is a stress hormone. Adrenaline, that's a fear hormone. It handles mineralocorticoids, so it releases like testosterone, which regulates your salt. So all kinds of glamorous things, right? So that's the endocrine system. All these different organs communicate with each other through hormones, and they control the activity of your cells, of your kidneys and your fat cells and your liver cells, all kinds of things. What's on the right? Cardiovascular system, exactly right, very good. The heart is very important, as we all know. We've all heard about how important the heart is, but the heart is really just a pump. The heart is muscle, a ball of muscle that squeezes and pushes blood through those tubes, those blood vessels, and that blood circulating brings all of the things that your cells need to maintain homeostasis, right? So circulatory system is one of the most important systems in the body. Well, it's hard to rank them, but really when you get down to the needs of a cell, what does a cell need? It needs glucose, it needs oxygen, it needs to release carbon dioxide. That is handled by the cardiovascular system. This is the customer service. There are all of the fluids circulating through the body, collects things that need to be taken away, delivers things that need to be delivered, helps maintain all of your cells at homeostasis. So that's very important, obviously. What system on the left? Lymphatic system is correct. Lymphatic system actually collects fluid from your tissues, returns it back to your blood when that tissue, in the process of collecting that fluid back, returning it back to your blood, it goes through all these little strainers, these little lymph nodes, and there's full of white blood cells. The white blood cells trap bacteria and other debris, things that don't belong, destroy them. So it helps maintain, protects your body from infection and so forth. So that's the lymphatic system. What system on the right? Respiratory system, very good. So that's obviously important for maintaining oxygen and carbon dioxide levels in our body. You have to make sure we have a certain amount of oxygen. Got to make sure you have a certain amount of carbon dioxide. You don't want to have too much, obviously. You can't, otherwise, if it didn't matter how much carbon dioxide we have, we could just hold our breath for an hour, right? But we can't do that because we need to release the carbon dioxide from our body. It actually, the carbon dioxide is, that you're going to see this in 2402, so I might as well mention it now so you can forget it and then be reminded of it later. Who here has carbon dioxide in their body? Show of hands. 1, 2, 3, 4 people are alive, the rest of you are zombies. Okay, that's right, more hands are going up. Good. Who here has dihydrogen monoxide in their body? Yes, that's correct. 1, 2, 3 people are not zombies. This is water, guys. You all have water in your bodies, right? Here's a fun fact for you. This is not in this class. You'll see this in 2402. Carbon dioxide and water mix all by themselves. They do this on their own. They don't have to be in a living body to do this. This happens in the ocean. Carbon dioxide and water mix to make carbonic acid. That's an acid, which means that by definition, if you have carbon dioxide and water in your body, which you all do, you have acid in your body. And in fact, the more carbon dioxide you have, the longer you hold your breath, aka, the more your blood acidifies. Which is always funny to me that people say, oh, you have to eat this food in order to detox your body. How does it detox your body? Well, it adds, it's alkaline. It removes acid from your body. It's like you can remove acid from your body by hyperventilating, right? All right, great, acid's out. That's literally how it works. Carbon dioxide, when you clear it, it causes more carbonic acid to be released back into carbon dioxide form. So your lungs are actually a big part of how you maintain the pH of your body at a certain amount, 7.4. That's how much the pH of your body has to be, your blood has to be. What do you think happens if your blood pH goes away from 7.4? 7.4 is the pH. What happens if your body goes away from that? You're going out of homeostasis, right? Which means that you are dying. Yes, exactly right. Good. And that long pause, often the answer is dying, right? So, yeah, so that's the thing. Homeostasis of what? Of pH. We maintain homeostasis of pH with our respiratory system. It's weird, but it's true. Our carbon dioxide levels in our body are directly linked to the carbonic acid of our body, which means that it's going to alter what our pH is just by how much we're breathing, believe it or not. All right, what's the system on the left? Digest system, good. What's that for? For food. Yep, digesting and absorbing food, exactly right. The star, now this is not until 24 too. The star shows small intestine, a lot of blood vessels, collects the actual nutrients, puts them into your bloodstream, carries that blood to the liver where it gets broken down and changed around. All that material then goes to all your cells. But of course, your small intestine can't do the job by itself. That's why we have teeth and tongue and salivary glands and esophagus and stomach. So all those other organs are very important for supporting the function of the small intestine, which is to absorb nutrients, because you can't absorb a hamburger. You actually take a hamburger, you can't absorb that. It's not going to work. It's not going to work because, and this is why those hot dog eating contests are so gross to me. They're like swallowing whole, like, stop that. I'm going to throw that up later. It's gross, right? Because only small molecules can be absorbed through the small intestine. Only tiny little molecules, individual molecules, like, they're very small. So full-on large blobs of food are not going to be absorbed unless they're broken apart first, right? So that's why we have teeth and the stomach and all that other stuff. So that whole system works together to move materials through our body, break them down, absorb them, everything. What's the system on the right? Urinary system, also sometimes called the excretory system or renal system. That is for removing wastes from the blood, right? From your blood. That's actually whatever's in your blood goes into your kidneys. The materials that you don't need go into your urine, and then that goes out of your body. Notice a big difference here. There is waste coming out of both of these systems. The waste that comes out of the urinary system is waste that was in your blood, right? So you eat something, it goes into your blood, it's absorbed, and then it ends up in your urine. It's leaving your body that way. The digestive system also has waste, feces, but that never entered your blood, because if it entered your blood, it would go in the small intestine, and then eventually your kidneys would take it out. But we're talking here, feces, material that never entered your bloodstream, it just passed right through, right? And so if you're looking for something you ate that's indigestible, that you're going to find in your feces. If you're talking about something you eat, smoke or drink, it's going to end up in your blood, then it will later go out through your urinary system. That's why they do, which of these two systems do they test when they test you for drugs? Urinary system, right? They don't take a fecal matter sample for drugs. That would be pointless, because if the drugs are there, they didn't get into your blood, so they didn't do anything to you anyway, right? That's why they do the urinary system. Also, that would be silly, but anyway. Okay. All right, and last one, we got two organ systems here, but they're really the same one. What do we got? Reproductive system, very good. This is the only system that does not directly maintain homeostasis, meaning you can have it all removed, and it doesn't kill you. Now, of course, that's assuming you move it surgically and not just with, like, a battle axe, Game of Thrones style. That would kill you. But assume you don't need it. Now, the gonads do secrete hormones that affect the rest of the body, but these organs are not for maintaining your life per se, they're for creating life, right? Humans, other human beings, and so that would be the function of these guys. You would cover them in 2402. That's the only system that doesn't help maintain homeostasis of parts of your body. All right, so do I have any questions over chapter 1? No questions? Okay. All right, great. I think, okay, so